Our fascination for physics began with its ability to describe complex problems using simple principles. Although quantum computing may seem reserved for only PhD students, its core ideas can be portrayed using simple physics.
Today's video will focus on solving a fundamental quantum algorithm, also known as Deutsch's problem, by building our own quantum computer.
A classical computer takes an input, applies a function, and produces an output using bits, which are only in 0 and 1. A quantum computer uses qubits. They exist in superpositions of 0 and 1, described by the state psi. These quantum states are manipulated using operations. When measured, the qubit collapses to either a 0 or 1. To create this superposition, we apply a Hadamard's gate to a basis state such as 0, producing an equal superposition of 0 and 1. This is the key idea we will connect to the polarization of light. To model a qubit physically, we use polarized light. Any polarized light wave can be described using two basis states, horizontal and vertical polarization. Any polarization state can be written as alpha horizontal plus beta vertical, where alpha and beta are horizontal and vertical amplitudes of the respective components. This has the same form as a qubit state, alpha 0 plus beta 1, if we define horizontal as 0 and vertical as 1. For example, 45-degree polarized light has equal horizontal and vertical components, like a qubit in equal superposition. Additionally, there is a type of filter called a half-wave plate. They work by shifting one component of the wave by pi radians, causing the direction of polarization to be rotated by 90 degrees. For example, a 45-degree wave will become a negative 45-degree wave once it passes through a half-wave plate.
Now let's move on to Deutsch's problem. We have four functions, and here are their truth tables. f1 of x and f2 of x are balanced, outputting 0 and 1 equally, while f3 of x and f4 of x are constant, outputting only 0 and 1. A black box called an oracle hides one of these four functions. We get one attempt to determine if it's balanced or constant. A classical computer might need to check both inputs to be certain. This problem can be solved using a quantum computer. We modify the function so that it encodes itself as a phase. We send in a superposition state, so the function acts on both 0 and on 1. If the function is constant, both parts of the state are affected in the same way, so the superposition state is plus 0 plus 1 or becomes minus 0 minus 1. If the function is balanced, one part picks up a minus sign, turning the state into 0 minus 1 or minus 0 plus 1. Let's look at our physical quantum computer. On the right, we start off with a laser. The light first passes through a 45-degree polarizer, which represents a Hadamard gate, and puts the light into superposition. In the middle is a black box, which acts like our oracle. Inside there may or may not be a half-wave plate representing the hidden function. f1 of x and f2 of x are balanced functions. They both contain a half-wave plate, so one component of the wave is shifted. Regardless, they both have a resultant wave at minus 45 degrees. f3 of x and f4 of x are constant functions. Their waves do not change in polarization, as both components of the wave remain identical to before. On the left, the light goes through a minus 45-degree polarizer, and then hits a detection plate, which shows our output. Here's what happens. If there is no half-wave plate, or there is a full wave plate, the polarization stays the same. The second polarizer blocks most of the light, so almost nothing reaches the detector. This is a constant function. If there is a half-wave plate, it rotates the polarization from 45 degrees to negative 45 degrees. The second polarizer now lets the light through, and it reaches the detector. This is a balanced function. With just one pass of light, we can tell whether the hidden function is constant or balanced. We have built a quantum computer, demonstrating how physics is accessible to anyone.
And this is why we love physics.
Thank you for watching.